Hello students, our next derivation number 4, again pertaining to Gauss law. Electric field due to a uniformly charged, infinitely big plane sheet. Plane sheet means it has just two dimensions, there is no thickness, right? So it's just a plane sheet, no thickness, remember. Okay, so this is a positively charged sheet, uniformly charged, right? Positive charge on the sheet. We are interested in a point P, and we want to find the electric field at point P due to this sheet. Again, this is a charge distribution, so we'll take help of Gauss law to derive this formula. Okay, first let's understand one new quantity, sigma. Sigma is charge per unit area. That means you take the total charge on the sheet divided by the area of the sheet. Okay, so now you can imagine, sir, how can we find out area of an infinitely big sheet? Understand, this infinitely big sheet means the point P where we are calculating the electric field, right? It is comparatively very near to the sheet as compared to its dimension. For example, if you take this smart board as a sheet, if I am trying to calculate electric field at this point, it is slightly away from the sheet. So from the distance perspective, this distance is negligible as compared to the dimension of the sheet, right? So again, charge per unit area is total charge divided by the area, you will get a quantity sigma, charge per unit area. Okay. Now let's take a point P dash which is symmetrically opposite to point P. That means if it is at a distance r, this is also at a distance r but on the other side. And then create a cylindrical Gaussian surface such that these point P and P dash are lying on the two flat surfaces of the cylinder, the two ends of the cylinder, and this is how the Gaussian surface is formed. This cylinder is penetrating through this sheet, imaginary cylinder. Okay. Now again, we are interested in calculating the net flux. For the net flux, we will divide this entire Gaussian surface in two parts. First is the flat ends, and the second is the curved surface. So let's focus on the flat ends. Since all the points on this flat surface, right, they are symmetrical with respect to the sheet. Sheet is infinitely big, right? So if it is infinitely big, all the points are symmetrical with respect to sheet. If all the points are symmetrical, that means net electric field has to be in the it has to be perpendicular to the plane of the sheet, so it has to be perpendicular to this flat surface, right? And the area vector would be like this. Similarly, here electric field would be like this, and the area vector would be like this. So in both these cases, the angle between E and A vector is 0. They are parallel to each other, right? And E is same everywhere. So I can take value of E at a certain point P and multiply it with the area. Same point P dash, electric field is going to be E Q because it is symmetrical, right? So if here it is E, here also it will be E. So the net flux would be E into A from this side, E into A from this side. Total flux would be 2 times E, right? So that is written here. Net flux from the flat ends is going to be 2 times E into A. E is the electric field at the point P and A is the area of the flat ends. Don't bother about the area because it's going to get cancelled anyways. Now come to the curved surface. On the curved surface, if you see, the electric field is still going to be normal to the plane of the sheet, like this. Plane of the sheet is going to be like this and electric field is like this. But the area vector is this time is going to be radially outwards, normal to the curved surface everywhere. So all the points of the curved surface flux would be 0 because electric field and the area vector are perpendicular to each other. So if I have to consider the net flux from this entire Gaussian surface, this curved surface is not giving me any flux. Only these two flat ends are giving, which is 2 times E. So the net flux would be 2 times EA. As per Gauss law, net flux equal to net charge upon epsilon naught. So 2 times EA net flux is equal to net charge. What is the net charge? Now let's come to see the net charge here. Only this much portion, this circular portion from which this Gaussian surface is penetrating through the sheet, right? So this circle, उसके अंदर का चार्ज तो नेट चार्ज है, because बाकी सब चार्ज तो बेकार है, because that is outside the Gaussian surface. So inside this Gaussian surface, only sigma into A, because if this area is A, this area is A, this area is also A, same cylinder. आप कहीं भी क्रॉस सेक्शन काटोगे, कहीं पे भी क्रॉस सेक्शन लोगे तो हर जगह ए ही होगा. तो यहाँ भी एरिया हो गया ए. सिग्मा इज द चार्ज पर यूनिट एरिया. Sigma multiplied by A is the net charge from this green wala circle. So that is a net charge. So net charge is sigma into A upon epsilon naught. Now A get cancelled, E is equal to sigma upon 2 epsilon naught. That is the net electric field of the sheet. Okay, in vector form, how do we write it? Like, let sigma upon 2 epsilon naught, no change in the value, we just give it direction by multiplying with by n cap. And what is n cap? N cap is a unit vector perpendicular to the plane of the sheet, going out from the sheet if it is a positive charge and going towards the sheet if it is negative charge. Because we know for positive charge electric field has to be away from the charge, right? So that point is still valid. It's just that it has to be normal to the sheet. Sheet के normal ऐसा electric field रहेगी हर point. If it is positive charge, it will be away from the sheet. If it is negative charge, it will be towards the sheet. Okay, so this is our small derivation. Thank you very much.